In the shallow waters of Chuuk Lagoon, a dormant ghost fleet holds an immense volume of heavy bunker fuel. This submerged hazard was forged in a single catastrophic window of violence. The mechanism was a highly coordinated aerial and naval bombardment. The resulting stakes represent an expanding zone of toxic contamination. In early 1944, the United States Navy deployed Task Force 58 to execute Operation Hailstone. Their target was a massive forward operating base holding elements of the Imperial Japanese Navy. The resulting strike devastated the assembled vessels and permanently altered the underwater cultural landscape of the lagoon. Dive bombers and torpedo squadrons initiated a systemic dismantling of the anchored fleet. Lethal strikes breached outer bulkheads and shattered engineering spaces. As primary hull integrity failed, massive displacement vessels lost buoyancy and sank rapidly into the lagoon. As the crippled hulls began sinking, the crisis moved below the surface. Downward momentum drove the crippled hulls into the seabed, collapsing compartments and sealing off lower decks. This rapid descent trapped heavy fuel oil, diesel, lubricants, live munitions, and on some wrecks, smaller or cargoed quantities of aviation fuel inside the steel framework of the dying ships. The operation concluded with around 40 ships sunk during Hailstone, with later wartime losses and site counts pushing the wider lagoon total higher. This staggering volume of submerged steel transformed the lagoon into a dense underwater graveyard. The immediate knowledge gained by naval observers was the sheer scale and fixed resting location of this newly created ghost fleet. The sunken ships lay scattered across the seabed, their operational status permanently extinguished. The resulting static environment presented a profound structural challenge. The sunken fleet ceased to be a military target and became a complex engineering anomaly. The initial configuration of the wreck site established a severe physical boundary. Substantial, unexploded ordnance remained within the dark interiors of the wrecked hulls. Torpedo warheads, artillery shells, aircraft weapons, and depth charges lay among twisted bulkheads and cargo spaces. This concentration of explosive material created an immediate hazard zone. The presence of munitions dictated a hard limit against routine post-war commercial salvage. Traditional methods of cutting, lifting, or breaching the steel structures carried serious risks of disturbance, detonation, and structural collapse. Any heavy intrusive force applied to the deteriorating hulls had to be treated as a potentially fatal act. Faced with this extreme physical risk, intrusive recovery was complicated by ordnance, unstable steel, cultural sensitivity, and later legal protection. The physical threat of the unexploded ordnance often outweighed the economic value of routine scrap recovery. The intact compartments held pressure and cargo residues, but they also shielded dangerous wartime material. Engineers and divers had to treat the ships as hazardous structures, shaped by their own wartime payloads, leaving them isolated by the physics of their destruction. The lagoon absorbed the violence and enveloped the shattered vessels in isolation. Over time, the heavy steel hulls began to interact with the corrosive saltwater environment. The immediate wartime loss had laid the foundation for a much longer and more complex structural timeline. The sheer density of the sunken ships meant that the problem could not simply be ignored or swept away by ocean currents. They remained exactly where they fell, locked in the sediment and slowly deteriorating under the weight of the water column. Although ordnance kept heavy salvage at bay, the longer environmental threat was beginning to emerge from inside the sealed machinery spaces and storage bunkers, trapped fuel. For decades, the submerged structures faced an era of unrestricted exploitation until a sudden, legislative reversal permanently locked the site. The immediate post-war period transformed the lagoon from a hazard zone into an unregulated industrial graveyard. This era was characterized by aggressive physical intrusion and artifact pillaging. Commercial scrap hunters and localized dive teams operated entirely without institutional oversight. They viewed the decaying fleet not as a protected historical site, but as a vast repository of souvenirs, brass fittings, loose machinery, ordnance, and salvageable metals. The damage was physical as well as historical. Dynamite fishing and ordnance disturbance damaged superstructures, weakened exposed frames, and accelerated corrosion around fractured steel. Divers systematically stripped accessible artifacts, removing brass fittings, navigation instruments, and loose machinery. Some broke through degrading bulkheads to extract raw materials or souvenirs, artificially accelerating localized collapse. This period of unchecked destruction stripped away layers of evidence, altered the visual geometry of the wrecks, and compromised parts of the submerged fleet. The rapid dismantling of the site eventually triggered an absolute institutional pivot. Authorities recognized that the unregulated human intrusion was destroying the environmental and historical context of the lagoon. In 1971, a sweeping legislative action reversed the operational reality of the site. The Chuuk Lagoon Monument Law designated the Japanese ships, aircraft, parts, and associated objects within the lagoon as protected state monuments. This single mandate legally converted the scattered ruins into protected historical resources. Many of the wrecks are also treated with the sensitivity of war graves because human remains are still associated with the sites. The 1971 legal baseline gave future investigators a clearer administrative line for what could and could not be disturbed. Researchers now had a protected, albeit still vulnerable, structural environment. The law reduced the legitimacy of dynamite damage, souvenir stripping, and scrap hunting, but enforcement remained difficult and human impacts did not disappear. The wrecks were not frozen in time. They were placed inside a protective framework while corrosion, diving pressure, and occasional disturbance continued. However, this same legislation imposed a profound, hard limit on any future mitigation efforts. The jurisdictional denial strictly prohibited intrusive salvage, artifact recovery, and any form of hull modification. The wreck sites were placed under an absolute no-touch directive. Engineers and environmental scientists could no longer assume that traditional investigative salvage methods were available on demand. Destructive work now required permission and had to be justified against heritage protection, safety, and war grave sensitivity. They could not simply cut steel for metallurgical samples or drill into primary bulkheads as if the wrecks were ordinary industrial scrap. The ships still held hazardous material, but industrial remediation now had to pass through heritage review, explosive risk analysis, structural fragility assessment, and war grave safeguards. Proposals for hot tapping, bracing, or oil removal therefore moved slowly, requiring permission before any tool could approach a bunker tank. This strict compliance regime fundamentally altered the nature of the engineering problem. The threat of massive fuel releases required precise structural data to predict when the primary holding tanks would burst. Traditionally, an engineer would measure this by physically testing the steel yield strength directly on the hull. Under the 1971 law, that direct measurement became impossible. The historical preservation mandate effectively trapped the environmental hazard inside an impenetrable legal vault. To map the threat without breaching protected hulls, teams pushed remote sensors to their acoustic limits, relying on sonar-assisted survey, diver inspection, photogrammetry, and later three-dimensional modeling. These tools swept the water column and visible steel surfaces, translating acoustic and visual returns into exterior models that established orientation, list, deformation, and visible structural breaks without heavy mechanical force. The non-intrusive survey campaign produced a practical external inventory. Earlier assessments flagged 19 wrecks as significant pollution risks. Later work widened the threat list, and teams plotted coordinates, structural footprints, and spatial orientation for priority vessels under strict heritage controls. However, this pure reliance on external acoustic imaging introduced a severe operational hard limit. Multi-beam sonar cannot see through solid steel. The sound pulses bounce directly off the outer hull plating, leaving the vast interior spaces completely dark to the sensors. The angle of the sonar swath meant that overhanging deck structures blocked the sound entirely, creating massive acoustic shadows where the hull curved underneath or where hatches opened into the lower decks. They could outline a massive oiler but not measure fuel volume, tank condition, or the uneven distribution of toxic liquid behind the plating. The inability to visualize past the outer hull plating established a rigid proof ceiling. Engineers knew the 19 priority vessels contained toxic fuel, but they could not mathematically verify the structural integrity of the interior compartments. The sonar could easily detect a collapsed upper deck or a massive exterior torpedo hole, but it could not reveal if an inner bunker bulkhead had rusted down to a paper-thin membrane. Without internal verification, the exact volume of remaining fuel and the specific failure points of the internal holding tanks remain totally unknown. The external map was geometrically perfect, but it was hollow. Predicting collapse inside a flooded iron vault required engineers to estimate corroded overhead steel, unresolved hull stresses, biological growth, storm movement, and weakened supports without treating the protected wrecks as ordinary test structures. To bypass this physical restriction, corrosion scientists deployed a strictly non-destructive methodology across the coherent main structures. They utilized advanced ultrasonic in situ measurements to read the integrity of the steel entirely from the outside. Operating under tight procedural discipline, divers carefully prepared microscopic points on the external hull, removing just enough marine concretion to expose bare metal. They pressed specialized high-frequency acoustic probes directly against the cleared iron surfaces. The instrument fires a sound pulse through the hull plate, measuring the exact microsecond it takes for the wave to bounce off the inner wall and return. This acoustic transit time gives the precise thickness of the surviving solid metal, entirely bypassing the rust layer. By comparing live corrosion readings against known steel behavior and historical construction data, the scientific teams achieved a critical positive knowledge gain. They established corrosion trends for major hull components. The data revealed the rate at which the saltwater environment was attacking the iron matrix and reducing the remaining sound metal. As the cross-sectional area of the steel decreases, its ability to hold static load steadily drops. This corrosion calculus produced a practical risk window. Large structural failures become more likely as the wrecks age, but the data still cannot assign a single failure date. However, applying this decay formula to deep internal bunker tanks immediately collided with a profound physical and ethical barrier. Penetrating deep inside the structures can force divers into zones of original destruction, collapse, darkness, and human loss. Inside wrecks such as the passenger and cargo ship Yamagiri Maru, divers have reported human remains in lower interior spaces. These remains mark the ships not only as pollution sources or steel structures, but as tombs. Under war grave protocols, investigators cannot touch remains, drive heavy equipment past them, or route rigid probes and hoses through narrow interiors without careful planning, permission, and supervision. Human remains do not automatically prohibit every survey or oil removal operation, but they make deep access slower, narrower, and more ethically constrained. The inability to navigate past these profound interior boundaries establishes a severe proof ceiling. While the external hull plating thickness is mathematically confirmed, the internal containment bulkheads remain completely inaccessible. The toxic bunker fuel behind these engineering spaces cannot be physically verified, and the inner oil tank walls remain unmeasured. Entombed personnel therefore shield the deepest environmental hazards from direct scientific measurement. The engineering team successfully measured the exterior shell and established the mathematical certainty of its eventual collapse. The coherent steel framework of the massive vessels is decaying exactly as the ultrasonic physics predict. Yet, while the main hull mathematical fate is definitively locked, the surrounding seabed tells a parallel, contradictory story. The physical distribution of detached wreckage resting on the exterior decks and the surrounding seafloor presents a stark physical contradiction. The resting geometry of the scattered objects entirely defies the violent kinetic energy of the wartime sinking. Heavy brass instruments, porcelain ceramics, and personal equipment are not dispersed in the random chaos expected from a massive explosive event. Instead, modern surveyors documented highly artificial debris arrays. On the broad upper decks of the Shinkoku Maru and other wrecks, loose artifacts have been documented far from their original operational positions. Heavy telegraph components, brass fittings, and fragile objects can appear clustered together, divorced from their original mounting points inside the ship. The pattern points away from a simple wartime blast, which might scatter, crush, or bury material, but would not neatly organize it for later recovery. Analyzing this displaced scatter yielded a clear positive knowledge gain for marine archaeologists. Artificial off-hull and on-deck distributions can be read as evidence of post-war artifact movement, souvenir collection, looting, and diver disturbance. The survey teams cataloged a disturbed cultural landscape showing that the wrecks had been altered by human hands after the battle as well as by the battle itself. While the clustered artifacts tell a story of human interference, the wider debris field sprawling across the dark seabed reveals a much more lethal scatter pattern. Wartime impacts, explosions, collapse, and later disturbance left munitions and hazardous cargo scattered inside wrecks, on decks, and in surrounding sediment. Surveyors identified unexploded ordnance and fuel-related debris that had to be treated as hazardous even when partly buried or visually obscured. This detached and exposed material imposes a severe operational hard limit on modern survey teams. The scattered ordnance creates unpredictable exclusion zones around the major target ships. Operating heavy remotely operated vehicles or placing environmental sampling equipment directly on the seabed must be planned around strict standoff protocols. Contact with unknown munitions is avoided, not tested. This scattered hazard restricts safe approach paths near the seabed. Surveyors can be physically blocked from establishing close proximity environmental monitoring stations in surrounding sediment. The footprint of detached debris dictates where acoustic, optical, and sampling vehicles can and cannot travel. Any attempt to sample the water column directly beneath hull overhangs must account for ordnance, fragile steel, snag hazards, and the risk of disturbing protected remains. Using strict visual standoff protocols, the scientific teams photographed and measured the scattered material without shifting a single submerged object. That work fixed the outer hazard perimeter, but it did not stop the central risk inside the remaining ships. The narrowing risk window defines the current operational reality. Non-intrusive and limited technical assessments have been consolidated into a priority framework for potentially polluting wrecks, giving authorities a structured way to rank hazards without claiming an exact rupture date. Within that framework, vessels carrying acute concentrations of trapped heavy fuel oil, diesel, lubricants, and hazardous cargo residues are treated as priority assessment targets, rather than as ships proven to be closest to a single terminal failure. The framework reduces operational ambiguity. It helps determine which submerged hulls require closer observation, targeted survey, limited oil removal, or emergency planning, and which regions of the lagoon face the greatest risk of contamination. Achieving this level of clarity represents a profound positive knowledge gain. Regional authorities and environmental institutions now possess a stronger threat matrix. This matrix enables targeted hazard planning across the atoll without requiring every wreck to be opened. Emergency response teams understand the resting depths, coordinates, visible condition, and priority ranking of the major targets. They can estimate spill trajectories based on local currents and prepare surface containment strategies customized to known wreck positions. Many unknown variables of the submerged threat have been narrowed, categorized, and placed into an institutional record. Planners know where the highest priority hazards are concentrated, which makes spill preparation more targeted even where internal conditions remain unresolved. However, possessing a stronger model of future collapse does not automatically grant unlimited authority to stop it. The management paradox of the potentially polluting wrecks framework remains severe. Identifying the environmental threat does not turn the wrecks into ordinary salvage targets. The strict non-disturbance boundary governing the protected site remains in force, and any intervention must pass through heritage, safety, legal, and environmental controls. The massive engineering intervention required to offload large quantities of heavy oil is difficult, expensive, and dangerous. Salvage ships equipped with heating systems, pumps, and hot tapping tools cannot simply breach the submerged plates at will. The governing policy has therefore favored targeted, carefully controlled intervention rather than unrestricted preemptive salvage. The inherent risk of triggering surrounding munitions, shattering a fragile bulkhead, or disturbing a protected grave remains high. Yet limited oil removal, technical surveys, and response planning have occurred where authorities and specialists judge the risk manageable. The result is a narrow operating lane, targeted action, not unrestricted salvage. Consequently, the present management condition of the vast underwater site is constrained, but not frozen. The present program therefore concentrates on monitoring, survey, modeling, capacity building, and limited intervention under strict controls. Investigative teams return to deploy tethered optical cameras, acoustic scanners, diver-based inspection, and three-dimensional modeling tools. Their primary task is to verify outward signs of collapsing steel, active leakage, and changing structural risk. They measure the increasing sag of main decks and document the slow buckling of vertical support frames, while response teams evaluate where limited oil removal or containment planning is justified. Their measurements feed decisions that can alter the risk only carefully, with full awareness of the fuel, ordnance, and human remains resting deep inside the lower spaces. This condition defines the final legacy of the survey missions. Investigators mapped structural limits, proved measurable decay, and isolated critical targets without leaving a mechanical scar on the protected fleet. Yet the underlying physical problem remains only partially resolved. The surveys define the threat, and limited interventions have reduced portions of the hazard, but much of the risk remains in place. Priority hulls continue to rest in dark water, with every physical decision slowed by fuel, ordnance, fragile steel, and protected human remains. Corrosion continues, some leaks have already occurred, and further releases remain possible. The priority framework remains an administrative warning system, not a guarantee against rupture. It tracks a continuing pollution risk already partly realized as the lagoon waits for the next release point to appear.